Good morning, good afternoon.
Hi, Alper.
Hello,
Good
Victor,
morning,
how are
Professor
you?
Alper. Good morning.
Good morning.
Good
Dr.
morning. Good
Jason. How are you?
morning.
Morning,
Good
Professor
morning,
Alper.
Dr. Omar. Good morning, Dr. Doha. Thank you. Thank you so much.
Good afternoon, everybody.
Good afternoon, Dr. Stephen. Welcome.
Hello, good afternoon, Professor Alper, everyone.
Hello, good afternoon, Dr. Yaman. My dear colleagues, just as usual, I'm waiting a couple of more minutes for our colleagues coming from the class and also the ones that might have a meeting or something. Good afternoon again, my dear colleagues. I believe majority is already joined. And welcome to today's session. It will be about structural equations modeling, and I will try to conduct a sample analysis using IBM SPSS AMOS software, which is developed mainly to analyze structural equations modeling. If you allow me, I'm gonna start my presentation, and then we will go through. Again, as always, please stop me and ask any questions that you want, or just write your questions on the chat, and I will try to answer it right away. Let me share my PowerPoint presentation first of all, and we will go through that one. Can you please let me know that if you see the PowerPoint appropriately, or?
I can see.
Yeah, we can see it.
Yes, we can.
Perfect. Thank you so much. Yes, as I just mentioned, today it's, of course, just an introduction to structural equations modeling, because it's a technique that has a heavy algorithms and mathematics behind it, and it's impossible to finish everything today. But mainly my purpose is to give you a kind of sense of what it is and how, in what purposes we can use it, what are the advantages, and hopefully we will have time to conduct maybe 1-2 examples using AMOS software. So structural equations modeling is what they call, based on the researchers, it's a second generation data analysis method. The difference is actually the first generation methods, as we know, this the regular multivariate analysis techniques such as t-test, regression, ANOVA, these things. And the most important limitation, the common limitation of those, what they call first generation techniques, is actually they can analyze only one layer of linkages between independent and dependent variables at a time. Or in other words, you can test one dependent variable at a time. So if you have more than one dependent variable, you have to build several models for each y variable, and then you test them differently. So by the introduction of structural equations modeling, actually this technique is not very recent, by the way. All the mathematics and all these algorithms and the approach behind it, it goes 1950s. However, as the analysis technique and as a software, it's not too old, let's say. SEM as a second generation method, main difference, have the ability to simultaneously analyze of models that have multiple independent and dependent variables at the same time. So, and also it encourages confirmatory approach rather than the exploratory approach. And I'm going to explain what I mean by saying confirmatory approach a little bit later. So SEM, we can utilize it for analyzing complex research models, like multiple associations between multiple independent and multiple dependent variables, again, simultaneously in one model. And we can even include mediating, especially mediating variables and moderating variables, if we can convert them into statistical conceptual, from conceptual to statistical variable. But mediating analysis, we can directly test it using SEM approach. SEM approach is based on a concept that we call latent variables. Latent variables is actually something that we cannot measure directly. However, we can measure them indirectly through measuring other observable characteristics. And usually these latent concepts are multi-dimensional constructs with several underlying dimensions, like commitment, for example. Commitment, as I used it, because I'm using the same example just to give you the chance to compare among the variables, because commitment is easy to explain, and also for the purpose of our statistical, let's say, workshop series, it's easy to structure and test using in different models. So in commitment, for example, we cannot observe commitment directly, right? So, but we have a method, we have a way to measure the commitment. How we are trying to measure the commitment? By asking questions in different dimensions and somehow merging them, combining them under the same concept and saying that, yes, we are measuring commitment. So commitment itself is a latent concept, actually. It's a latent variable. We don't observe it directly. So, but we observe it, we kind of measure it using or through these several dimensions at the end of the day. So in social science, we have a lot of examples like this, like satisfaction, like usefulness, like attitudes. All these are like we cannot, or stress, we cannot directly observe it, but we measure it indirectly through these several underlying dimensions. So the approach that structural equation modeling is used is actually based on this latent conceptual approach. So these latent concepts, as I mentioned on this slide, often, not always, but often measured with data based on the perceptions, based on the self-report, most of the time. So that is why you see this latent concept usually in social science when you use different type of questionnaires, surveys, try to measure different things. However, by using those measurements, we are using them to understand the magnitude or scale of these latent constructs. It is also used in experiments and some other type of research. However, again, it's very popular and beneficial method, especially for research using surveys and questionnaires. So again, latent constructs, as a conclusion, these are abstractions about a phenomenon that cannot be observed directly. So they don't have a tangible existence. We cannot see it. Like we can measure, we can measure time, we can measure length, we can measure weight, right? We can count something. However, these things are tangible. We see it, we measure it directly. There is no suspicion, there is no vagueness about these things. And it's a universal. If I say it's 5 minutes, it's 5 minutes for everyone in the world. Doesn't matter, right? So it doesn't change. But however, when you measure something like latent constructs using perceptual or using items based on the people's perceptions, it might give even different results from time to time. That's why we discussed about reliability and validity before about these things. So latent constructs have indicators associated with them. So we have some measures. We can call it approximations. And then these empirical indicators, these tangible measures, help us to understand the magnitude of the latent construct again. And usually more than one item are required for each construct dimension. In structural equations modeling, actually, mainly what we do step by step is first, we specify our model based on previous knowledge, based on previous literature, or also based on our hypothesis, also built using the previous research literature and theories. So we already know the model and we specify the model. And the second step, we identify the model using the parameters. Now, specify a model, meaning that we are using theoretical constructs, but when we identify the model, now we are trying to explain how we measure these constructs using parameters, such as factor loadings or path coefficients and these things. And then we estimate our model. We measure, we have a set of model fit parameters. I'm gonna talk about them. I'm not gonna have time to explain each one of them one by one, but I'm gonna talk about it. And then you will, let's say, compare this model fit data, and then we will understand, we will conclude if our model is a good fit or it needs some improvement to make a better fit for our research. So this is how we use, in general, step-by-step structural equations modeling approach. So the major applications of SEM, using all these steps in maybe slightly different in detail. However, we use SEM for causal modeling or path analysis to explore the cause and effect relationships between the variables, okay, including mediators and moderators, as I mentioned before. And second major application of SEM is confirmatory factor analysis. Remember, we discussed exploratory factor analysis in one of our sessions previously. And I mentioned at that session something that saying that if you have a data and if you're not aware of a structure about the factors, then you should go with exploratory factor analysis. The purpose was to explore the structure, to find out the structure based on your data. However, I also mentioned that if you already know from the literature, based on a prior theory, prior research, if you already know the factor structure, then you might need to go with confirming your model with the, if it fits with the prior model or not. So this is why we mainly use confirmatory factor analysis. So for this purpose, we actually use structural equations model. We can also use SEM for second order factor analysis, which is a little bit more advanced analysis method, and covariance and correlation structure models, and especially when it's like a group comparisons like we do in ANOVA analysis. So what are the main advantages of SEM? Why we need it, or why it is this popular? First of all, it provides more flexible modeling, especially the softwares that employs structural equations modeling, that I'm going to also mention the names of those software a couple of minutes later. Most of them provides you visual modeling, as Amos do. That's why that's one of the main things that I like about Amos. You can model your research, your hypothesis visually, like drawing your variables and then drag and drop the data in it. So it provides a much more flexible modeling. It allows distinctions between observed and latent variables that we don't do in other regression models, especially. So we just use factor analysis, but what we do is just measuring and taking the average. But here we do have this distinction, which brings us to ability to modeling the error terms also. And we can test the models overall versus individual coefficients, meaning that we can have a simultaneous analysis of the whole picture without any dividing any kind of way or splitting our model in any way. So we can test models with multiple dependent variables simultaneously. Also, the overall independent variables, including mediators and moderators. So it allows us to model error terms, as I mentioned, and also it has the ability to test coefficients across multiple between subject groups. So if our sample has different groups, and if we need to do a kind of comparison like we did in ANOVA, see? So we can also compare our model, our research model, our model of our hypothesis also across multiple subject groups. When we model SEM, there is two type of variables. We already talked latent variables and observed variables. However, we also have two. It's not just for SEM, by the way. It's also these two types of variables actually comes from this causality approach, comes from the path analysis approach. So the first one are exogenous variables. In parentheses, it's independent variables, by the way, is IV is independent variables. Variables which are of external origin. In our model, they don't depend on any other variables in the model. So we just measure them and we just accept that, okay, it is as they are. So the reason of their size or magnitude, it depends on something else. So we call them independent exogenous variables. And endogenous variables, which are dependent variables in our model, is actually which are of internal origin, meaning that the variance in these endogenous variables actually depend on the other independent variables in the model. So this is two main differentiation of the variables that we use in SEM. Visually, when you see a SEM model figure, we usually use this square-wise or like rectangles to present observed variables. Okay? So when we measure something directly, we use this rectangle to display. And latent or unobserved variables, constructs, are shown by using this ellipse figure, ellipse shape. Direct effects is used with arrow with one side arrow, and reciprocal effects is shown by two-sided arrows, and correlation of covariance is shown by using this kind of arc having two arrows in each end. So this is the visual that is being used SEM. In SEM, we have two modeling also using these different type of variables. We have a measurement model and we have a structural model. Measurement model actually is the most important feature of SEM, and it's dealing with how latent variables are connected to its indicators. So which indicators actually measuring which latent variable. So the measurement model is something like this. Okay, so it is shown visually when we model SEM. It's being shown like this. Again, I'm using the same example. In this one, organizational commitment, as I just tried to explain before, is a latent constant. So it is not measured directly. So that's why it's shown as an ellipse. And we have observed variables, effective commitment, continuous commitment, and normative commitment, asking specific questions in a questionnaire format or as a survey. That's why they're observed by the researcher. That's why they are shown as rectangles. And for each measurement, one of the most important features of the structured equation modeling, when we model it, we also add this error for each observed variable, because we, as a researcher, accept that we might be making some errors, some mistakes in our measurement. So these errors might be systematic errors. These errors might be just random errors. These errors might be just fixed errors. But there, there are three types of errors. But we model them in the structural equation modeling by making this link to each observed variable. So this is a measurement model for SEM. Okay, so it shows us how we measure a latent construct. A second type of model is structural model. Actually, it's a combination of the measurement models. It's a set of all exogenous and endogenous variables in a research proposal, in a research model, with all errors, connections, and all disturbance terms or error terms in the model. So let me show you an example of structural model. As you see here in this example, we have 5 different latent constructs. In this model, these 2 variables are actually causing a variable which is a mediator in our model, which mediates the relationship, and it is causing, it's related to 2 dependent variables simultaneously. So by using SEM, we can analyze this with 1 click compared, opposed to the SPSS or routine regression models. So in this structural model, you also see that for each latent construct are measured by different measures. You see, for example, for the one on the left upper corner, it was measured by 3 factors or 3 questions, measure 1, measure 2, measure 3. And these 3 observed measures, actually, when it combined, it's measuring this latent construct. The others, every one of them is measured by different, let's say, observed variables. And then at the end, by using this analysis method, all in all, with 1 click, I can test how these measurement items can measure their constructs. At the same time, we also measure the significance of the relationships in this whole model with a mediator in the middle. So this is an example of a structural model. As you see, structural models are composed of different measurement models, which shows us how one actually latent construct is measured. Okay? So when it comes for a couple of points related to structural equation modeling, one is sample size requirements. Usually, of course, more is always better. However, structural equation modeling, due to its heavy mathematical calculations and statistical assumptions behind it, it requires a little bit more sample size. Okay? So in theory, of course, again, it's not a universal rule, and more is always better. However, what they say, you have to have at least 200 samples to have, let's say, a robust results from your SEM regression approach. When we try to understand how our model fits, so we use a couple of measures, and I just listed the most important ones here, which are the chi-square test is one of the most important ones. We have comparative fit index. We have root mean square error, Tucker-Lewis index, goodness of fit index, and also there are lots of others. However, again, when you go through the academic articles using SEM, you will see that mostly these are the most common measures understanding the level of fit of a structural equation model tested. There is also another one here I would like to mention, which I'm going to show you using Amos. There is also another measure which chi-square test or chi-square parameter divided by the degrees of freedom gives us also a measure for model fit, which is one more important. So just to again, one of the most important use of SEM is confirmatory factor analysis, as I just mentioned. Now I just would like to show you what is the difference between these exploratory and confirmatory factor analysis. You would remember, I just put this as a reminder of exploratory factor analysis. You know, in this one, in EFA, as a researcher, we do not specify the structure. We just try to explore it and we just try to find it out. So we assume that all factors are correlated. All factors might be affected by the other factors. And errors are uncorrelated, of course. So it is something like this. Remember, when we have the output from SPSS, we were seeing the factor loadings of each item with each factor, and we were choosing the ones which has the most or which has the largest factor loadings, and we were, let's say, loading those items on their relevant factors by just checking their factor loading parameters. Like, so we were assuming that all of them are. So we don't have any idea at the beginning. We just try to find out. On the contrary, in confirmatory factor analysis, okay, we have an approach and we also know how the relationships should be. We has the ability to decide and to implement a prior knowledge. And we already know how the factor structure should be. And then we are trying to confirm if our data give us the same results with the literature. This is the purpose of CFA, actually. So let me show you a visual representation of CFA. In CFA, we don't assume that every item is correlated with the others. We just assume that every item should be correlated with its own latent factor. Based on what? Based on our prior knowledge. And when we enter this model, and then we check the fit parameters, model fit parameters, and we realize or we explore if my model really really fits with the same factor structure in the literature, in the theory. Again, this is just a simple, again, representation of both together to show you the difference a little bit better. So as a final word for presentation part, SEM, for SEM, you know, SPSS, first of all, doesn't have the ability to conduct structural equation modeling analysis. So that's why there are other softwares that has the ability to do that, starting with the ones that I like most, because I use it personally, IBM SPSS AMOS. AMOS is actually also developed by IBM and copyrighted by IBM SPSS. However, it's a separate software, it's a separate program. It's not a part of SPSS or not a macro in SPSS. It's a complete separate program, software that was developed to conduct structural equation modeling. And there is LISREL, there is EQS, and there is M+, and there is R. Actually, personally, I didn't have any experience with LISREL and EQS, so I cannot say anything about them. However, M+ and R, I have some experience with those two. And I can say that M+ is also the most, let's say, disadvantage of M+ and R. You need to write a little bit of code to conduct the analysis. However, in M+, it's a little bit easier. And R is a kind of programming language as you know, it's also widely used in data science, and due to their very rich libraries, and you can conduct almost every type of analysis using R. And another advantage of R, of course, it's free because it's open code software, and it's completely free. You can download directly, and you can use it again for free for your analysis. And recently, I also realized that there are a couple of interfaces, let's say, developed that runs R behind them. And if you make your search, you can even find these nice GUIs, let's say, graphical user interfaces, for recently developed for R. So that is the end of my first part of my presentation today. Is there any questions from your side? About, again, there are lots of things to talk about SEM. And when you go in details, there are covariance matrices, there are error terms, there are calculations, but again, there is not enough time. So that's why the purpose of this presentation is to just to give you a hint about what it is, how we can use it, what are the main characteristics and advantages of SEM. So now I would like to, I don't see any questions, or am I missing something? Let me check one more. Okay, I don't see any questions. And if I may, I would like to go to the second part of today's session, which is a practical example using Amos. For that purpose, first of all, I would like to share my screen, and then do you see my whole screen, my dear friends?
I'm sharing the team screen. So.
Okay, perfect. So now on my computer, I am now running Amos graphics. As you see, IBM SPSS. Do you see that it opens up now, the interface or GUI of the Amos?
Yes, yes.
Yes.
Perfect. So this is Amos, what we call, again, it's a software developed to conduct structured equations modeling technique. So let me make it a little bit bigger. So it's also like very similar to SPSS interface and also the Windows structure. There are menus on the top, file, edit, view. The most often that you are going to use are the ones which is view, analyze, and of course there are a couple of tools that you might need to use. There are also some plugins which makes your life easier when you develop and test a model. Now, today, I would like to conduct a very simple analysis and to show you how we can develop it. I will try to make it as slow as possible, but because of the time constraint, I also need to be a little bit fast flow approach, let's say. And because there are, again, lots of things to talk about it, and I don't even need to mention it, but my door is always open to anybody that might have any kind of question if you want to apply it in your research or if you want to just to explore the software or the model. So the first thing that we need to do here, actually, from the file menu, we need to choose data files. Data files, when you click them, there is this small window opens it, and from there, by clicking file name, we need to choose the file which has the data in it. So usually, actually, SPSS files, the files which has the .sav extension are the ones that you use in Amos, which also gives you a lot of flexibility when you are using it. So I prepared this data, the sample data for you. Now I'm trying to go to that data, SAS training, SEM, yes, some example data set. When you click it, you see directly here how many variables in it. Now it's just 32 entries. Again, it's just a sample data set that I tried to prepare very quickly. But again, just as a reminder, in theory, it should be at least more than 200 to give you a fairly robust results at the end of your analysis. But for this data set, we only have 32 entries, and we click OK, but just that we also have a chance to group the variables if we have a subgrouping option, but we don't have it now, so I just click OK. So now we upload our data into Amos. How can we be sure about it? If you go to the view, and if we click list variables in dataset, as you see now, I see all the variables in my sample dataset that I just upload to Amos. There are these tools on the left, as you can see, visual tools that you can draw a latent variable, you can draw an observed variable, and also to make your job easier to move objects, to delete them, to click and choose any one of them here. On the bottom part, there are shortcuts to calculate the estimates, to show you the analysis properties, and to show us the results in text format. Now again, for just as an example, I would like to analyze two latent variables. I would like to analyze the causality between them, and each latent variable is measured by 3 observed items. So we are gonna see the results. Okay? Now for that purpose, I am going to draw a latent variable together with their observed. Amos gives you a lot of practicality when you try to draw this. For example, when I just click, first it draws the latent variable. When I click again, it adds this observed variable automatically. And 2 and 3. As I told you, in this example, I have 3 observed variables. And by using this, So now I would like to draw another one. Which again has 3 observed variables. So these are, now I'm going to analyze the causality between these 2 variables. So we are going to define one of them as dependent variable, the other is as independent variable, and we will see if there is any relationship between them. We can also draw separately, my dear colleagues, just to show you, I can draw a latent variable separately, and I can add by using this observed variables to my latent variable if you want. So I just want to take it back, or let's use the delete option. I want to delete these because they are not going to be analyzed, and yes, I want to delete this. In Amos, don't forget to click back to go back from your we have nice visual techniques. For example, if I click this and if I click our variable, it takes the variables on left side or right side. And just to make for us a little bit easier, I'm gonna make it like this. And for us, now I want to draw this causality line. I'm saying that the upper variable is independent and lower variable is the dependent. Now I want to mention something here. When I create latent variable and when I click to add them observed variables, the system adds one more thing on top. These are the error terms for each observed variables, as I just mentioned in my presentation. Now, as you see, it's very easy to draw your model visually, and it gives you a lot of flexibility because you see visually what you really test in your model. So how are we gonna upload the data? How are we gonna define which variable is measured with what and where is the data? So before going there, when you click each variable, there's a small window opening and you can give the variable name. I give you this independent variable only. You can give a variable label. You can also define the font size and everything from here. And I can add this. I can say that dependent variable just for the moment purpose of this. And one of the best or most beneficial feature of AMOS, when you click, remember we clicked variables in dataset. So, and then you can just drag and drop the variables to the observed variables, which are rectangles, right? Let's say that the first one we measured with this AGY1, AGY2, and AGY3 is used to measure our IV. And we have PY1, PY2, and PY3 to the other one. And we have one more step, my dear colleagues. It is the naming these error terms. You can name them by clicking one by one, or there is another very nice feature of AMOS. When you go these plugins on the top, and when you click name unobserved variables, when you click it, as you see, the system named them automatically, starting from E1 going to the last one, E1, E2, E3, E4, E5. So just one also reminder, if you want to write a lot of things and if you don't see it visually, you can draw a big latent variable, and when you click it, its observed variables also be in the size relative to the one that you draw. So if you want, you can also do that to make your job easier to make your analysis. So when we all complete them, the last thing before going to the analysis, we need to go to view and analysis properties. When we click analysis properties, there are lots of things to talk about here. But mainly, we need to check maximum likelihood because it's usually the default method for SEM. If you want the system estimate means and intercept, you can click this one. And this is also selected default for, let's say, a medium advanced models, it's enough. And there is a numerical part, a little bit advanced subject, biasing part, we call it unbiased and maximum likelihood. And when we click output, what I recommend, click on the first 4 on the left part. It gives you minimization history, standardized estimates, correlations, and sample moments. And also, you can click residual moments and modification indices. And I also want to click indirect effects, and that would be it for today. Modification indices, I would like to mention what it is, because the others you might just guess. For the standardized estimates of the coefficients, indirect, direct effects, like I mentioned in mediation analysis. Modification indices gives you the idea of which, so if you do a kind of modification to the model, which modification gives you what enhancement in your model's fit, or if you are going to lose a little bit from the level of fit of your model. So it gives you analyze one by one for which modification is going to give you what. Are you going to earn something, or are you going to lose something? So I'm just closing right now, so I'm ready for the analysis. So the first thing, before going further, I need to save my path diagram. I'm just going to save it again in my same stats training SAM folder. Sample model 1. And to analyze, to run the analysis, what we need to do is here calculate estimates, or you can do it from here, calculate estimates. When we click it, you see the system did the analysis here. So it's finished without any error. So to see the results, either you can click sorry. You can see the results as text. If you want to see the results on the figure, you have to go up and you have to click this part, view the results on the virtual. As in our example, independent variable is significantly related to dependent variable with 0.38 coefficient. If you want to see the results, for now I can see the coefficients, but I don't see if the model is fits or significant. I need to check the just next to the save button. I have a button that helps me to see the results as text. You see there are these analyses of the summary, notes for group, variable summaries gives us the variables, sample moments gives us the covariances and correlations, and there's a button notes for the model. And there is a button here which is most important, is model fit. When we click model fit, you see all the model fit parameters for our model. First, I would like to show you the important ones. The first one is this chi-square. Chi-mean is chi-square analysis. Chi-square parameter is measured as 29.2, and df is 9 for this model. Okay? And they calculate chi-square divided by df. To have a significant model, we prefer to have a value less than 3 for this chi-square divided by df. Chi-square is small due to our small number of samples. If you have a large number of samples, you expect, of course, a large chi-square. I will show you a couple of parameters which will give you the idea about your model fit. This is GFI. We always check the default model, okay? Not the saturated model. We are checking the default model. And for GFI value, for a best fit, it should be close to 1. So if it is larger than 0.9, it's very good. If it is larger than 0.8, it's acceptable. So our value is 0.77. It's very close to 0.8. We might accept it. For CFI value here, it's also the same. We are expecting a value close to 1. So the closer to 1, the better the fit is. So we see 76. It's not a perfect fit, but it's okay to some extent. Another important one, which might be the most important among them, is this RMSEA value is the default model. It is 0.269. This value, this RMSEA should be low. Actually, for a good fit, we expect this value to be lower than 0.08. Okay? I again want to mention this. We expect this value to be less than 0.08. So when I check this, it's 0.27 almost. So it means that our model needs a kind of revision or some links, some estimated or proposed links are insignificant that might cause this problem. So if you have these problems, you might drop some of the connections. You might change some of the causalities to make your model to be fit based on this fit criteria. There is also this modification indices that gives you a kind of idea, meaning that it says that if I connect PY2 to PY1, I will gain something for my model fit. So this is a very basic example of how you can apply SEM using AMOS. I hope it gives you an idea. Of course, again, the purpose was not to give a whole lecture in detail and all the features of the AMOS, but it was to give you an idea of how we can use it, what are the main features of AMOS and structural equations modeling. I hope it helped you to understand what it means and how you can use it. I see. Okay. Any questions or anything that you want to add, my dear colleagues?
Too much information for me to process at the moment, but thank you very much. I need to go back.
Thank you, Dr. Yaman. Thank you so much.
Thank you very much. Very helpful, of course, the example and the software itself is very helpful as it looks like. So thank you very much.
Thank you so much. And again, I mean, if you want to apply it in your research on any time, I'm here. I'm just one phone call away. Thank you so much.
On behalf of the research committee, Professor Alper, I would like to thank you for your excellent work in the past several sessions regarding SPSS, as well as Dr. Faden, of course. And definitely this gives us room for some for future iterations, let's say, of these trainings to go more into details actually of these topics. So definitely a topic for us and a thing for us to consider in our future meetings of the research committee. But definitely thank you so much for your excellent work one more time.
Thank you so much, Dr. Vladimir, for your kind words and for your support as always. And I'm glad that I hope it's going to help our colleagues to have, even if I contributed a little bit, I would be more than happy. Thank you so much again for your kind words. Thanks a lot.
Thank you very much.
Thank you,
Professor. Thank you.
Thank you, Professor.
Thank you, Professor Alper.
Thank you so much, my dear colleagues. Thanks again for your attendance. Thank you so much. Thank you.
Thank you, Professor Alper.
Thank you, Ms. Alex. Thank you so much.